In this lesson, we will build an intuitive picture of the Wheatstone Bridge, what it means for the bridge to be balanced, and how to solve for an unknown resistance by a simple ratio. Here is the classic 4 resistor bridge. 2 resistors on the top branch, our sub 1 on the left, and our sub 2 on the right. 2 resistors on the bottom branch, our sub 3 on the left, and our sub X, the unknown, on the right. A sensitive detector. The galvanometer connects the midpoints. We call the left pair one leg and the right pair the other leg. At balance, the midpoint on the top has the same potential as the midpoint on the bottom, so no current flows through the galvanometer. That condition leads to a simple ratio. Our 1 over our 2 equals our 3 over our x. We can rearrange to solve for the unknown. Our x equals our 3 times our 2 divided by our 1. Here is the simple 4-step measurement procedure. 1. Choose known resistors R1, R2, and R3. 2. Adjust one of the known resistors, often R2, until the galvanometer reads 0. 3. Record the values at balance. For compute our x equals R3 times the ratio R2 over R1. Why is this so accurate? We null the current through the detector, so the meter's internal resistance does not matter. Also, the result is based on a ratio, so supply voltage changes cancel out. And modern bridges are extremely sensitive. Common applications include precision resistance measurement, strain gauges in load cells, and temperature measurement with RTDs in a bridge. Let us do a quick example. Suppose R1 is 100 ohms, R2 is 200 ohms, R3 is 150 ohms, and the galvanometer is balanced. We place those values on the diagram. Then compute our x equals R3 times R2 over R1. That is 150 times 200 over 100, which is 300 ohms. That is the Wheatstone Bridge. Balance the 2 legs, read 0 current, and use a ratio to find the unknown resistance.